All right, welcome to our second lecture on two-sample t-test. This one is on dependent samples t-test. So you might be asking, when do we do this? We do this when we have two samples and the standard deviation is unknown. And what makes this different from an independent samples t-test is that the participants are matched in some way. So there's two basic ways this might work. One is you might match them on some other variable. So for example, let's say you're looking at how a new teaching intervention, how effective that is, how it affects learning. But you say, boy, I wish I could control for IQ because I'm worried that's going to have a big difference. That's going to account for a lot of the variability. So what you might do is say, okay, I got two classes, the experimental and the control. And what I'm going to do is rank the kids here for intelligence and rank the kids here and then do a one-to-one matching. So I'll match the two most intelligent, the second two most intelligent, and keep doing that for all the kids in the experimental and the control. That way, I'm then comparing pairs, and these two participants are roughly the same intelligence, just as these two are, etc. So that's matching on some variable, in this case IQ. The other thing we see often is a before and after design. So a classic weight loss study. You look at Homer and some other participants before and after going on a certain kind of diet and see if there's a difference. So let's look at an example. Say the North American Bacon Council tests that participants change weight after 6 months on an all-bacon diet. So the independent variable is what diet they're on, normal or all bacon. The dependent variable would be weight. So we're going to have some new symbols. D bar is the average difference score. And I'll show you where we get those difference scores just in a moment. But that's a sample statistic. It's trying to estimate mu D, which is the average difference score in the population. And SD bar, the standard error of the mean difference, that's the measure of the variability of the sample means, the sample difference scores, average difference scores around mu D. Okay, so how would this work? We're going to first here look at D bar and mu D. So let's imagine that we have the weight before and the weight after a diet. And these are the people that are matched, or either they're the same person. So somebody before weighed 180 and now they're up to 210. So what's the difference here? 180 minus 210 would be a difference of negative 30. And we could do this for each one of these. This minus this gives us the difference scores. So these are all individual difference scores, or you could say Ds. And then if you add them up and divide by, 7, you get the average difference score. And so that's D bar. So when we're doing this on the computer, SPSS will calculate this automatically. And just to state again, this is the mean difference score in the sample. Now, what's going on at the population level? The null hypothesis is going to be that there's no difference between before and after. In other words, we would set mu D equal to 0. So we're supposing that in the long run, the differences here would average out to 0 if there really is no true difference. The alternative is that there is some kind of true difference. Either people gain or lose weight would be what the alternative specifying. One other note, the degrees of freedom, it's still n minus 1, but since people are paired now, it's the number of participants in just one group, or the number of pairs minus 1. So in this case, 7 minus 1 is 6. Then we have the dependent T formula, and there's a new standard error that we're going to clarify. So we have the average difference score in the sample. That's the D bar we just calculated. Then it's the average difference score in the population. And you'll like this. That's always going to drop out because for our purposes, we're always going to specify that as being equal to 0. You don't have to do it that way, but that's generally what happens, and that's the only case we're going to look at is where this is always set to 0. So then you just have D bar divided by standard error of the mean difference. Now, be careful. Before, with independent t-test, we had standard error of the difference. Now we have standard error of the mean difference. And it's indicated by having the D with the bar over it. So that's the variability in average differences that you'd expect just by chance. So remember, the top is always the difference that we observe, and the bottom is the difference we would expect based on good old sampling error. Now, just as a point of reference, this is basically the same as the one sample t-test. Here, we're dealing with D's, and before, we dealt with sample means. And we could, if we wanted to, indicate that this is x bar minus mu x bar. So this is just a special case of the one sample t-test where we're dealing with different scores rather than just x's. So how would this go into SPSS? We're going to have two columns, and for each person, we're going to have both of their scores on the same line. Or if they were matched people, we'd have each score for each person that's matched on the same line. Look, and if you think back to an independent t-test, this is different. Independent t-test, we had in the first column what group somebody was in, and the second column their score. Now we have the DV, the actual scores, two to a line. So that's a big difference. And when you get ready to run the dependent t-test, it's fairly easy. You just got to analyze, compare means, paired sample t-tests, pull over the variables you need, and you're off. Okay, what would the output look like? You are going to have the following here, and what I'd like you to do is take a shot at labeling what these are based on the symbols we just talked about. So label these two things and these four things down here. And notice down here, just to give you a hint, these are all the paired differences under this heading that you're dealing with. So hit pause and we'll come back here in a second. All right. So how does this work out? The mean of the paired differences, that's the observed mean, that's just D bar. Standard deviation is SD. Standard error of the mean difference would be SD bar. And then over here we just have P for the same significance test we've been doing. And up here we'll just note that this would be X bar 1 and X bar 2. We don't have to use that per se, but I just want you to realize what's going on up here. These are not different scores. These are the actual means in the two groups. All right. And then if you have a significant difference like we do, then we have to calculate the V statistic, the effect size. So this tells us the T statistic, the p-value associated with that, tells us that the difference we have is reliable, that there is some kind of treatment effect, but now we want to know how big it is. So here is our D formula. And you'll notice the top is, like before, just the difference between the two means. And since we've made mu D equal to 0, it's really easy. It's just the observed difference score is on the top, and then on the bottom, that's our standard deviation of the difference scores. Not standard error, but standard deviation. And then we work that out and get the 1.1 something. So again, you're always going to set the mu D equal to 0, so it's always going to drop out. And again, notice also that we have the negative disappearing because we're taking the absolute value. You'll never have a negative D over here. Now, just FYI, I showed you the X bars on the previous formula. There's two ways to get at this difference mean. You can either do it the way I showed you or get the means for the two groups and subtract them. But either way, it'll work out to 15. So there's two ways to think about the D formula. Either way, you're going to get the right result. The simplest thing to do is just to take the mean difference score here and divide by standard deviation. All right, the hypothesis testing steps. Number one, we're comparing X bar 1 and X bar 2, where mu and standard deviation unknown. That's just like for the independent t-test. The null hypothesis is that mu D is equal to 0, and the alternative is that mu D is not equal to 0. These never change if you're doing a dependent t-test. Usually we have alpha equal to 0.05. The degrees of freedom, again, are the number of pairs minus 1, so in this case 6. And we would look up T critical based on this information, and it equals 2.447. So, based on the SPSS output, we get a T obtained of negative 3.074, and then we have to see if that's significant. So if we're doing it by hand, we could compare this to T critical, and does that exceed T critical? It does. On the negative side, it exceeds that 2.447. Of course, if you're doing it on the computer, you can just look at the significance value, the p-value, and see that this is below 0.05, so it must be significant. So that leads us to reject the null, and then we have our paragraph. We would say the research hypothesis was supported, the weight of subjects before the all-bacon diet, blah, was significantly less than the weight after, blah, and then summarize the statistic. T with 6 degrees of freedom is equal to such and such. The effect of diet on weight was large. D is equal to 1.1619. And just to be clear, as you might surmise by having somebody eat an all-bacon diet, that the scores before are lower than the scores after. And that's why you have a negative T, because you're taking this minus this bigger number and it makes it negative. Okay, then we have a second example here for you to work on. Go ahead and try to write up the paragraph that you would get from this. And hit pause, and when we come back, we will look at your answer. To just give you the scenario, let's say we're comparing people on the grip strength of their right hand versus the grip strength of their left hand. And we will get, and you will have the paragraph here to look at momentarily. So hit pause and try to do that yourself. All right, coming back. Here is your paragraph. You'll notice that the hypothesis is supported because we have the significance value below 0.05. And so we'd want to compare the two groups. So participants showed significantly more strength in their left hand compared to their right. We'll give that one. And then we summarize the statistic. T with 28 degrees of freedom is equal to such and such, comma, P is lesser than or equal to 0.05. And again, we're just looking at the sig value here, which is telling us that it's significant because it's below 0.05. Because it's significant, we need to do the D statistic. So again, that's just the sample difference score divided by SD. So we plug in the average difference score here and divide by SD, this one here, and we get a D of 0.4256. So we say the effect of side, that's our independent variable, which side, on strength was small. D is equal to 0.4256. Next, we'll do a review of the one sample t-test. So the question is, do depressed people have more nightmares? And let's assume normal people have 1.5 per month. So you have some output here. What you want to do, explain the outcome of the analysis and include the D statistic if appropriate. So just doing the paragraph is fine. So go ahead and hit pause, and then when you're ready, hit play again. If you look here, the significance value, it's below 0.05, so we know it's significant. And we need to calculate the D statistic. So this would look like the hypothesis was supported. Depressed patients have more nightmares than normal people. Mu is equal to 1.5, comma, and then T, 10 degrees of freedom, is equal to 2.547, comma, P is less than or equal to 0.05. And then we would figure out the effect of depression. A number of nightmares is large. D is equal to 0.7682. And again, we just take the difference between the sample mean and mu, and then divide that by standard deviation on the output, and that gives us the D value. So remember, there's always three parts. First, was the research hypothesis supported? Then the means and the statistical test, and then if it's significant, the effect size statistic, the D, is that last sentence there. So the last two slides, just some review of some important concepts that we've touched on before, the difference between samples and populations. So samples are described by statistics. So capital M or S, the letters of the regular alphabet are statistics, and then the parameters are parameters characterize populations, so that'd be your Greek symbols like mu and sigma. So Remember, the statistics are trying to estimate the population parameters. So an example here would be Winthrop University SAT verbal scores. Let's say that this is our population that we're going to draw from. And you typically don't know this, but if you were God or some all-powerful being, all-knowing being, you would know that the mu was 493. Typically, however, what researchers are doing is just taking samples out of these populations. So here's a sample of 6, and we figure out the sample mean for that. Should make sense. It's not exactly going to estimate mu correctly. It's going to be hopefully close. But there's going to be a difference. The difference between population mu and sample mean is sampling error. And that's what, in your t-test formulas, that's what goes on the bottom. That's the difference that you expect just based on sampling error. And that's just based on sampling error, and that's always some measure of standard error. If we draw another sample of 6 at a time, you're going to get a slightly different sample mean. And you'll get a distribution of these sample means around this mu. So the key takeaways is almost every sample is going to have some sampling error. We hate sampling error because it makes it hard to tell if any difference is due to a treatment effect or some kind of intervention that we've perhaps done, or whether it's just that background noise. So in an experiment, we typically don't know the population parameters, and we have to make inferences based on the sample means. So if you imagine an experiment where you're trying to improve reading scores, we have a control group and an intervention group, the intervention group being the ones that were treated differently. Let's say we take 5 from each population, and we have their scores on the reading test. And we may determine that it looks like the scores from the intervention group are higher than those from the control group. But of course, the problem is we don't know if this difference is reliable or if it's significant. We don't know if there's a treatment effect, which means, in other words, we don't know if this population mean for the control group truly differs from the population mean of the intervention group, or if this difference is just a function of sampling error and these two population means are actually the same. So we're trying to determine if the population means actually differ, or if the result is just based on sampling error. So every time you do hypothesis testing, you're trying to decide if it's just sampling error, it's just a function of the variability you get anytime you take a set of scores from a population, or if there's really truly a difference between two populations, if these groups represent samples from populations that have different population use. So it's got to be one of two things. Either the difference is due to sampling error, or the difference is due to a treatment effect.